Iterating fast with Vega Lite API, Application Programming Interface. We will discuss the landscape of tools for data visualization at various abstraction levels, including D3, React, and Vega Lite API. Setting up a Vega Lite API template visualization, and iterating visualizations fast. We're going to fly through the design space of data visualizations using marks and channels via Vega Lite API. I like to think of the landscape of data visualization tools as a pyramid. At the bottom of the pyramid, you have what I call low-level tools. With low-level tools, you need to put in a lot of work to get a visualization to appear. But then you have full control over every detail. You can do things like add customizations, tweak things, and add interactivity. And then towards the top of the pyramid, there are high-level tools. These tools let you put in just a little bit of work to produce a lot of visualizations that have quite a bit of variety. But with high-level tools, you sacrifice some of the customizability and ability to add complicated interactions because you don't control every detail. They're kind of like black box systems. Examples of low-level tools include HTML, CSS, SVG, JavaScript, and DOM APIs. You can create things with just these tools, but it's going to take a really long time. At a higher level than this comes D3. D3 lets you move faster and is quite powerful, but it's still a lot lower level than some of the other tools out there, such as Vega. Vega is a tool that lets you declaratively specify visualizations using only a JSON configuration object and not really writing any JavaScript code. Vega Lite is an even higher level of abstraction than Vega, and it sort of fills in defaults and it lets you produce visualizations with much smaller configuration files. Vega Lite API is a JavaScript API for producing Vega Lite specifications for visualizations. I would say this is higher level because it lets you write very, very concise and small code to produce entire visualizations. Along the same sort of level of abstraction of D3 comes React, and also Angular or other frameworks. On top of a React, there's a medium high-level library called VX that lets you compose visualization primitives. And there's another library using React called Semiotic by Elijah Meeks. This is a pretty high-level API for producing visualizations. Another popular library is raw graphs. In the Python ecosystem, there's a thing called Altair, which is actually a wrapper of sorts around Vega Lite, and it lets you produce Vega Lite specifications in Python. And it's quite similar to Vega Lite API. Altair and Vega Lite API are quite similar to ggplot2, which is sort of the original high-level API for producing visualizations. Even higher level than this, you have commercial tools like Tableau, where you can produce visualizations without writing any code at all. It's just drag and drop. Tools at a similar level of Tableau include Microsoft Power BI and ClickSense and Tibco Spotfire. Plotly is another popular one. In the Python world, again, you've got Pandas, a relatively low-level tool for doing mainly data manipulation. And then there's Matplotlib. I would say that's at a medium level of abstraction. And on top of that, you've got Seaborn, another Python library that has functions to create sort of canned visualization types. There's a compelling lineage here that traces back to The Grammar of Graphics, this book by Leland Wilkinson, published in 1999. This book, The Grammar of Graphics, explains an actual grammar in the sense of a language, where you can compose this kind of algebra of specifying how data maps to graphics, and it's all very well structured. Unfortunately, these ideas did not have any open source implementation for people to use. So that led to Hadley Wickham reverse engineering these ideas from the grammar of graphics to produce ggplot2, and that's why it's called ggplot, grammar of graphics plot. ggplot2 is the tool of choice for R developers who need to produce a bunch of different varieties of visualizations in a relatively short amount of time. ggplot was introduced around 2007, and then that inspired the development of Vega by Jeff Hare and his team around 2014. Vega is also based on the grammar of graphics, these concepts. One of the problems with Vega is that it was a bit too verbose to use, so then Vega Lite was introduced around 2017. And very recently, in 2019, Vega Lite API was created by Jeff Hare. That's where Vega Lite API sits in the context of all these various tools. And Vega Lite API is what we're going to be working with today. Vega Lite API is a relatively young project, but I think it's super promising because it's based on Vega Lite, which is very well established. And look at the code you can write. This is ridiculous. You can create a whole visualization just by, this 4 lines of code. This is what really defines how the data is visualized, and everything else is what I would call plumbing, just to sort of hook everything up and make it work. There are many examples of Vega Lite inside of Observable. Here you can see, for example, the code for this map. It just says, all right, make a mark square, where the marks are squares, use this data, transform, predict, encode, use color based on this digit, set up some configuration, and then render it. What I ended up doing is sort of reverse engineering what's going on here, plumbing-wise, and made it work in VizHub. Let me tell you about this Vega Lite API template, which produces this graphic from this code. This is the visualization specification using Vega Lite API. The idea here is you could fork this template and mainly just change this to iterate very quickly on visualizations. But how does this work? Well, let's start from index.html. We're including a bunch of libraries, including Vega, Vega Lite, Vega Lite API, Vega Tooltip to make tooltips work, and D3 just so we can fetch the data and inspect it. This CSS here is to make sure scroll bars don't show up. This CSS here is a customization of the tooltip. See, when you hover on these, a tooltip shows up, and I had to customize it a little bit because the original style made it really tiny. In the body, we're including bundle.js, which gets built from index.js. This is what I would call the plumbing code that hooks everything up and makes it work. We're importing the various libraries that we need, and we're importing this config from config.js. This is just some appearance customization to improve readability. For example, getting rid of the domain line, which is this thick line at the bottom that I don't really want to be there. Making the tick color the same as the grid lines. By default, they're a slightly different color, which I don't really like it. And then this style customization is really just to make the font bigger. This is the default, and in this particular environment, it's a bit too small. So that just makes the font bigger and sets the color of the text to this dark, not quite black value. That's what our config.js does, which we're importing here, and we're also importing getData. GetData.js is just a function that loads in some data. We've got our CSV URL, which is pulling from gist, GitHub gist. We're importing CSV from D3 and then using async await to fetch our CSV file and get it into this variable called data. And then, and this is really why I'm using D3 here instead of Vega's built-in data fetching functionality, you can look in the console to see what attributes you have available. This is printing out the first row of data, which we can take a look at right here just to see which attributes are available and some example value for each one. Vega Lite API has a feature where it can fetch the data for you, but when I was actually trying to develop with that, I found it a bit frustrating to need to go outside of this environment to figure out which attributes are available and what are their example types. So this is why I structured it this way, so you can just console.log the data, and if you need to do any processing of the data, like filtering or transformation, you can do it right here in JavaScript before passing it in to the Vega Lite API. And then this async function returns the data. So that's what getData.js does. So we import getData, and we're also importing viz from viz.js. And this just contains the specification of the visualization itself. So in index.js, after we've imported all that stuff, we call VL, Vega Lite API, .register, and this sort of hooks up Vega Lite, and it says we should use SVG as the default renderer as opposed to Canvas. And by the way, I chose SVG here so that you could do things like full screen it and you won't lose any resolution. See, if we change this to Canvas, it's going to essentially render an image comprised of pixels. And then when we full screen that, it gets a little bit blurry, and the blurriness would come through if you wanted to, say, print this out. So that's why I chose SVG as the default renderer. But if you have a lot of data points, like more than 10,000, switching from SVG to Canvas would help performance for sure. SVG sort of gets bogged down when there's more than around, 10,000 shapes. And then here's the logic that makes the tooltip work. And then down here is the run function. This asynchronous function extends our visualization definition to provide it the data that it gets from awaiting the invocation of getData. It also sets width and height to be the size of our window. It sets up this auto size thing to make sure the visualization fits properly inside of the box that we give it. And then it passes in the configuration that just customizes the visual appearance, which is from our configuration module. And finally, it takes that specification and renders it. And the .render function is an asynchronous function, so we need to await its result, which is a DOM element. I think it's a div that contains an SVG inside of it. And then we append that to our body element. That's what ultimately adds the visualization to the page. And lastly, we invoke the run asynchronous function to kick off the whole process. All right, that's what our Vega Lite API template looks like. Now let's get to the fun part of iterating fast using this Vega Lite API. In viz.js, we've got our visualization specification. Let's break it down a little bit. I'm going to remove some things that are not strictly necessary at this moment so we can see what the bare minimum looks like. We're importing VL from Vega Lite API, and VL is the conventional name for use with this API. And there's a bunch of stuff on it that we'll use as needed. The whole specification starts by specifying what mark type is this. For example, it could be mark point, it could be mark line, and see how the visualization updates just like that. It could be mark area. But for this data, mark line and mark area don't really make sense, so I'll just keep it at mark point. And then the stuff that we pass to the .encode function specifies the channels for this visualization. VL.x says, okay, this is going to be our x position, and we set the X position to a field Q, meaning a quantitative field, a field with numbers in it. For example, acceleration. And the same thing for Y. We're setting the Y position to be a quantitative field, horsepower. By default, these quantitative fields use a zero baseline. And in the case of our scatter plot, I don't really want it to have a zero baseline. So we can say .scale and set 0 to be false to avoid the zero baseline. And we've done it now for our X position. See now, acceleration starts at 8 instead of 0. And let's do the same for our Y. Now horsepower starts at 40, and the points sort of spread across our display. One really neat thing about Vega Lite is you can specify a tooltip encoding as part of the channels. And it's not strictly a visual channel because it's interactive, but I find this very powerful. You can say, set up a tooltip, field N, meaning field nominal or categorical, name. In this case, the name of each car. Each point here represents a car. So if we hover, we can see the name of the car or the model. So that's our basic setup. What we're seeing here is the default encoding of the point mark, namely a little blue circle that has an outline and no center. We can customize that by what we pass in here to mark point. For example, we could say fill true to make it filled in, and see it's filled in with, looks like black. To make it just circles, we can say stroke is false. Now we've just got some black circles. Additionally, we can customize the size of this to be, say, 100. I think size here refers to the area. We can change size to get bigger or smaller circles. We can also set opacity to, say, 0.5 or 0.2. This makes the circles semi-transparent, and I like this trick of setting the circles to be semi-transparent and also setting a large size because it gives you a clear sense of the density of where the points are. And I'll just reformat that long line. That's how you can customize the appearance of your marks. But notice how the visual encoding itself, the combination of marks and channels, didn't actually change at all. We only customized the style of the marks. Let's see what fields are available in our data. We can compare any two of these with each other just by changing what we pass in. Right now we've got horsepower versus acceleration, but we could just as easily say horsepower versus displacement, and we get a totally different picture. How about horsepower versus year? We can just paste year right there. We can see that in more recent times, there are no super high horsepower cars. That's kind of interesting. Notice how our labels for year are not quite right because it's interpreting the field as a quantitative field, but it's a little more subtle than that. It's actually a time field, so we can say field T, and Vega will interpret it as time, and then we get these perfectly good labels for our years. Let's say we want to analyze horsepower versus MPG versus something else like origin. Which country did the car come from? We can map origin to color like this. vl.color.field n for nominal origin. We're getting something that doesn't quite look right. I think it's because we are overriding the fill here. And if I get rid of that, okay, it's working, but really what I want to see here is filled in circles. So let me get rid of this stroke, and I think we can say mark circle. All right, now we've got some circles that are colored by origin. And now we can do some tweaks, tweak the size and the opacity a little bit, make it pop a little bit more. Let me make these a little bit smaller. And we can join this line together now. So what is this really telling us? Red here means USA, and it looks like USA have a lot of high horsepower, low MPG cars. We've got Ford, Plymouth, AMC, Oldsmobile, Chrysler. And the other two colors are Germany and Japan, and we see a lot of Japanese cars with high MPG and low horsepower. Interesting. It looks like there's quite a bit concentrated around this hot spot here. This looks like sort of a sweet spot balance between MPG and horsepower. And that's where we find the likes of the Honda Civic and Toyota Corolla. But anyway, that's how we can encode another channel with color. With scatterplots, we can encode yet another channel using size. And that looks quite similar to X and Y. I'm just going to take that structure and swap Y with size. And now, see that? We get a legend here that says horsepower, and these are the sizes that correspond with the various values. Here, horsepower is redundantly encoded with both Y and size. So let's see, what else could we visualize as size? How about weight? I'll just put weight in here in place of horsepower. It looks to me like weight corresponds pretty closely to horsepower. If you ever find yourself asking, though, what is the correlation between, or the relationship between this and this, you can just plot them against each other in a scatter plot to use the more powerful channels of X and Y position. It's a lot easier to see differences in position than differences in size. So what was that question again? What's the correlation between weight and horsepower? Well, we can just exchange MPG with weight and find out. All right, check it out. That's pretty well correlated, but there are some outliers. What is that outlier there? Buick Estate Wagon. Interesting. It has a super high horsepower, but it's not really that heavy as you would expect for that horsepower. What's this other outlier that has higher than normal horsepower? BMW 2002. And now weight is redundantly encoded with both X and size. So I think I'll change size to be MPG. Here, color is representing a categorical or nominal attribute, but color can actually also represent quantitative attributes. Check it out. If we just take this field Q of weight and we assign it to color, what happens? We get this color scale that varies in luminance, where the darker values are the higher ones. Also, X and Y don't necessarily need to represent quantitative attributes. They can also represent categorical or nominal attributes. For example, origin. We can change weight here to origin and then change field Q to field N. And look at what happens. In this view, we can see very clearly that the US has more high horsepower cars than Germany and Japan. If that's all you want to see, though, you really don't need color and size. So I can just delete those, and we're left with this. We can have a little fun and tweak these marks. I'll go back to mark point. And what if we make these super huge and then more transparent? We can make them way bigger than that, actually. And I'm noticing that scale 0 false doesn't really apply to origin. And we could remove it from this one too to make the circles go a little further away from our labels. I'm curious to see the density more clearly. So what if we go back to mark circle and change the opacity to be very low? Interesting. That's how you can iterate quickly through scatterplots, but there are more types of visualizations than just scatterplots. Let's move on to a different data set to explore some other types of visualizations, like line charts and area charts. I'd like to try to make this visualization with Vega Lite API. This existing visualization hosted on blocks.org is backed by a GitHub gist. So I'm going to click this link here, and then in the GitHub gist, I should be able to find the data file. Here it is. And then if I click raw, here's the URL we can use to load in this data. So I'll go back to our code over here. To make it load different data, I'm going to go into getData.js and change CSV URL to be that new URL. Now we can take a look at the first row of data for this other data set. We only have two attributes, temperature and timestamp. Armed with that knowledge, we can go into viz.js. I'd like y to be temperature, and I'd like to use timestamp as x. So I'll put that right there. But that's not a nominal field, that's a time field. So I'll use field t. And it looks like that worked. We can tweak this to make it a little more readable. These opacity values from before don't really make sense. So I'll set the opacity to 1 and the size to be, say, 90. All right, now we've got this scatter plot that represents changes in temperature over time. And I see our tooltip is not working right. Maybe let's set the tooltip to be temperature. Now we can read what the temperature values are. To make this into a line chart, we can just change mark circle to mark line. Oh, but now the size is off. What if we set size to be, 5? All right, we've got a line chart of temperature. And if we change line here to area, we can make it an area chart. How can we make this bar chart in Vega Lite API? Let's give it a try. I'll pull in the data by going to the gist, scrolling down to the CSV file, finding the raw link, copying this. See, this data set just has country and population. I can change get data to use that new URL, and then change viz.js to use those fields. Country is one of our fields, and I'd like country to be the x-axis. So I'll paste that here, but it's not field T anymore, it's field N. All right, our axis showed up. And then the Y field should be population. So I'll paste that here, and that is a field Q, quantitative. But we're using mark area, and that doesn't make any sense at all because there's no connection between these adjacent countries here. So this is a nonsensical representation. We can change mark area to mark bar, and now we get a bar chart. And I'll change our tooltip to show population as well. I would like these bars to be sorted, though. Let's see how we can do that. If you Google Vega Lite sort, we get to this page on sorting. And what we want to do is sort by another encoding channel. We want to sort X by the value of Y. And it looks like we can just pass in sort to the encoding field. So let me try that. I don't know exactly how that translates to the Vega Lite API. But what if we tried .sort Y? All right, it worked. And then we can use -y to get the same bar chart that we had before. How about this stacked bar chart in Vega Lite? Again, I'll get at the data behind this. Scroll down to the CSV file, click on raw, grab this URL, and use it over here in getData.js. What I'd like to do here is set the religion to be represented by color. So in viz.js, I think we can just add another field, vl.color.fieldN, and pass in religion. All right, now we've got that stacked bar chart. With this sort of data, I'd like to try also a different encoding where the y-axis represents a religion, and then the size could represent the population, the number of people in that country that adhere to that religion. To do that, we could take this field and religion and set it to be the y field. Now we've got this grid of country by religion. Color is redundantly encoded with y, so I don't think we really need color, but I'm going to use size here and set size to be population, which should be a field Q. I don't think size works well with mark bar, but let me try mark circle. Interesting. Well, the majorities pop out. In Brazil, you can see it's majority Christian. Indonesia is majority Muslim. US is majority Christian and unaffiliated. But this is a lot more sparse than I would have imagined. But hey, you don't know until you try. So I encourage you to do the following. Fork any one of these, modify it to load in your data, and just play around. See what comes out. That's all for Iterating Fast with Vega Lite API.